Okay, let's take a look at this guy here. This is second order. We have a second derivative. It is linear because all of my y's, y primes, and so forth are linear functions of y. We don't have any y squared. We don't have e to the y, nothing like that. It is homogeneous because it equals 0. And it has constant coefficients because all the functions in front of the y's are just constants. If I had a 6x here, it would not be constant coefficients. Okay, so we know how this works. We know we assume y equals e to, I'm going to use t as my variable here just to mix things up here. Y prime will be lambda e to the lambda t, and y double prime lambda squared e to the lambda t. These are all lambdas, no x's anywhere. Okay, and then we plug all those in. Again, we're going to get to the point pretty quickly that we can jump straight from here to our characteristic polynomial. But for completeness, let's write everything down here. So I'm plugging all three of these guys in to the appropriate places up here. We factor out that e to the lambda t because it is a common factor. And we're left with here our characteristic polynomial here in the brackets. Remember, this guy never equals 0, so we can just divide it out. And here is our characteristic polynomial, lambda squared minus 6 lambda plus 9 equals 0. Again, once you get good at this, you can jump straight from here to here. The order of the derivative will match the power on lambda. Second derivative, lambda squared. First derivative, lambda. No derivative, no lambda. All right, that guy factors lambda minus 3 squared. That's a perfect square trinomial. We only get one solution. We have a repeated root. Write that prettier. We got to do something a little fancy on this one. So we just get lambda equals 3 and 3. We get the same thing twice. We have a second order DE. We need two linearly independent solutions to get our general solution. Remember, independent is the good kind. I can't do y1 equals e to the 3t and y2 equals e to the 3t. Those are not, that's the same solution twice. Those are not linearly independent. Those are dependent. So what do we do when this happens? We tack on an extra t. If I had gotten here lambda minus 3 to the 12th, if I had a 12th order differential equation that had a repeated root of 3 12 times, then I would just keep tacking on powers of t until I had a total of 12 of them. So I would have a t, then a t squared, and then a t, all the way up to a t to the 11th. And that whole list would be my list of 12 linearly independent solutions. Now we could go through and check. We could check the Wronskian. Remember, the Wronskian determines if functions are dependent or independent. The Wronskian. So, like, just to refresh your memory, we would put the two guys here, and then we would put their derivatives here. And we would check the determinant of that, and you'll see that we would get something that is not equal to 0. 0 is bad. If you get 0 from the Wronskian, your set is dependent, and you're not going to get a full general solution out of them. These are independent. Like, go ahead, you should check that. Plug those in here, check the Wronskian. You will not get something that is identically zero. All right, so we have our general solution then. Our general solution is C1 e to the first guy plus C2 e to the TE to the, yeah, the second solution there. Anytime we have repeated roots, this is what we're going to do. Just tack on extra independent variables. If we were using X, that would be an X. And that's a good place to stop.